Hi. So today in this video, we're going to talk about a nested interval theorem. Okay, and that's a also a very important theorem in the in our series regarding the topology in the Euclidean space. Okay, so and that's very close related to the closed set, right? That we just introduced in the couple of videos before. Okay, good. So before we start, let's give two lemmas. Okay, that will be pretty useful for this nested interval theorem, and then we'll introduce what is that theorem. Okay, so let's have some notation for it. So we're gonna say this J, okay, is an interval, okay, that is a closed interval or closed set. So it is from A to B, okay. So, and we use this L to denote the length of this J, okay. So this is the length, so that's in just a one-dimensional interval, right, in Euclidean space. So this would be defined as B minus A. So that's the length of the interval. So then we're gonna use two lemmas, and those are very, although they're called lemmas, but those are very straightforward. So lemma one that we're gonna use for later is saying that if 2 points x, y in this J, okay, then we're gonna say the Euclidean distance between x and y, or the absolute value of x minus y, that has to be less than b minus a, okay? All right, and this is pretty obvious, right? So we're gonna just skip the proof for this, okay? You can work on that if you're interested. And then I'm gonna give a lemma 2. So it's saying that we're gonna let this AB, this closed interval, to be a subset of a larger one, CD. Okay, then we're gonna have the order of those points. So that C should be the smallest, right? And then A, and then B, and D. Okay, this is also pretty straightforward. Okay, good. So then here it goes for this nested interval theorem. So theorem, this is called nested interval theorem. And it's important that this is only true for the closed sets, okay? So we're just talking about the closed sets, not open sets here in this video, okay? All right, so let's define again this J, but we have some little n. So this Jn is defined to be a closed set from An to Bn, okay? And this is in R1, okay, such that Jn plus 1 is subset of Jn, okay, for all n. So this is a natural numbers. But so what do we mean by this definition of those Jn's is that we have those sort of nested intervals, okay? If we have, so because here we have for a larger subscript, we're gonna have a smaller interval, right, than before. So the with the larger subscript, this interval will be nested inside of the previous one, bigger one, okay? So that's what we were talking about here. So, and the argument for this theorem is that then we have, so they're nested, okay? So what we have is that this intersection of those Jn, this is not empty. Okay, there's gonna be at least something inside of this intersection. Okay, good. And that's, we call this part 1. Okay, so the part 2 of this theorem is that we can say something further. Okay, so let's say if furthermore, so we assume that, so the limit of this length of Jn, if that converges to 0 as n goes to infinity, then we can also say something about that intersection. So that intersection, as we have this limit, so that contains exactly 1 point. Okay, contains exactly 1 single point. Okay, good. So this is pretty interesting, right? And when we see something contains exactly 1 point, right, then this must be very useful when we try to prove things later, right? Okay, good. So yeah, so let's try to prove, right? Okay, so yeah, so we just combine those together. So now we can first notice that we have this in the argument, right? So we note that this a n plus 1, b n plus 1, that's going to be a subset of a n, b n, right? As we mentioned, as the starting point of this argument for all n. Okay, and in particular, we have this a n less than or equal to a n plus 1, right? And b n plus 1 is less than b n. Okay, and this is for all n, right? Okay. And we're going to also observe that if we have, let's say, some number s greater than or equal to r, then this js is a subset of jr. Okay, so let's write those in order. So we're going to have js, okay, which is the smallest, or the smallest one, right? So that would be contained in js minus 1, and so on and so forth. And we're going to have some jr plus 1, but that'll be, the next will be jr. Okay, all right, so we can list this in order, and then we just use lemma 2, right? So then we can say something about the boundaries, right? So using lemma 2, and then we're gonna have AR less than or equal to AS less than or equal to BS less than or equal to BR. Okay, right? And in particular, we have AS less than or equal to BR. Okay, all right. So that's something we have, and then we can call some E as the set of left endpoint of Jn. Okay, so it means this E, okay, is some set, okay, those elements A, such that in R1 this A is a n for some n, right? That's it. Okay, so this E is not empty, not empty. Okay, so it means that we're gonna have this in R1, so it means we're gonna have this a n here, right? A1, A2, and B2, B1, Bn. Okay, so next we're gonna claim that bk, okay, is an upper bound for the set E for each k. For each k. Okay. That is an less than bk for all n and k. Okay. All right. So if k less than or equal to n, then we know that this an bn is contained in ak bk. Okay. And also an less than or equal to bn less than or equal to bk. Okay. As we see in this picture, right? So you can just have some mutation of this, right, from this proof. And then if k is greater than n, so that's the other case, right? Then we're gonna have an less than or equal to ak less than or equal to bk. Okay, and this is also this is the second half, right? So those two exhaust all the possibilities. Okay, and then this is done, right? Okay, good. So, and to take step further, right? So we're gonna have something else. So by the least upper bound property or axiom, okay, least upper bound axiom or property, okay, so there exists, let's say, some C in R1 such that C is the sub of E. Okay, so next we'll claim that C is in Jn for all n. Okay, and this is not hard to see, right? But we're still gonna try to argue this. So since C is an upper bound for E, we have an less than or equal to C for all n. Okay, and further, since each Bn is an upper bound for E and C is the least upper bound for E, so we can see that C is less than or equal to Bn. Okay, therefore we can conclude that an less than C less than or equal to Bn, or C is in Jn for all n's. Okay, and so we know that C is an element of the intersection of Jn. Okay, all right, so and then this part is finished, right? So for the next part, we're gonna assume that the length goes to 0 as n goes to infinity. Okay, so for the second part, assume length of Jn goes to 0 as n goes to infinity. Okay, so from the first part, we know that intersection is not empty. Okay, so we can make some points inside of this intersection, let's say we have 2 points, okay, but we're going to show that x equals to y. So we claim x and y, they're the same. Okay, and this is also a very nice way to prove this kind of argument, right? So for, okay, right, so since x, y, they're in Jn for all the n, because it's in the intersection, right? So this means we have the distance between x and y, this is less than or equal to the length of Jn, right? As we mentioned previously. And if this goes to 0, and then that distance goes to 0, okay, as n goes to infinity. So this has to be 0, okay? It cannot be negative, so it has to be 0, so x is exactly the same as y. And then we complete the proof, okay? Good, so then this kind of nested, so this is kind of the so-called the nested intervals, right? And we have all those closed intervals, they're nested together. So from here we can see something that is quite useful, that if we have those nested intervals, then we can say something about the intersection of that, right? So it's not empty, and we also further show that if the length of that goes to 0, and then we can show that this contains exactly 1 point, okay? This is a very useful and interesting argument, and might be useful for some analysis that we might see in our studies, right? Okay, good. So that'll be everything for this episode.